Hello, this is the video presentation for the machine learning project for Group 21. Our topic is to predict New York City taxi trip durations. This is a competition on Kaggle. Our team consists of 5 members. It is Ryan, Yusuf, myself, Jay, Abhinandan, and Zhenyan. So again, the idea is to build a model that predicts the ride durations of taxi trips in New York City. 2 datasets are used. The original dataset from the competition is on the left. It is simply the taxi trip duration dataset with the following features. And the second dataset is based on the first dataset, but has been run through an optimal path routing system to find steps within the paths of the most efficient trip from the starting and endpoints of the original data set. And the features are also listed on the right-hand side. So the first step was to conduct some exploratory data analysis. Here are some select analyses that we have done. More details are included in the reports. So the first thing was to look at the trip duration distribution. We found that with the exception of very few outliers, most of our trips were less than 3,600 seconds. This represents a very homogeneous data set, which is advantageous for our training. We also looked at some pickup times according to different days of the week. We see that during the weekdays, from Monday to Friday, there are peak pickups during the time of going to work, during lunchtime, and around dinner hours where people get off work. During the weekends, we see a high peak after midnight, between hours 1 to 2. And this is surprisingly consistent throughout the weekdays and also the weekends. A heat map is shown here of all the trip start points and end points. Brighter colors signify more pickup points in the same location. And we can see here that the streets are very clearly visible, and most of these pickup and endpoints are centering around the island of Manhattan, with the exception of Central Park, in which there are almost none. We used the interquartile range method to eliminate outliers. And this is applied to all of our features. We have tested both the interquartile range and the standard deviation methods, and we have found that the interquartile range netted better results. Data points which are more than 1.5 times the interquartile range away from the 25th percentile and the 75th percentile are deemed out as outliers, and they are removed from the data set. Some extra features are extracted for both the gradient boosting and neural network methods that we will discuss later. The features extracted are the daytime features such as the weekday, the hour, etc. From the raw timestamp. We have extracted these features because we found from the previous exploratory data analysis some important patterns relating to particular weekdays and particular hours. Principal component analysis is performed on the longitude and latitude variables because most of the data points are centered around Manhattan, which has a grid-like pattern for the streets. And the grid pattern of the streets does not match exactly the longitudes and the latitudes. So performing principal component analysis allows us to take advantage of this variation according to the street grid. The Manhattan harvest line distance of the trip is also calculated. The harvest line distance is essentially a straight line distance on a spherical object. So essentially this takes into consideration the curvature of the Earth. And of course the Manhattan distance is the sum of the vertical and the horizontal distance. The OSRM method is used to calculate the theoretical shortest path from the start points and end points given the map of New York City. The method also produces a list of segments of the fastest path between those 2 points. So each segment would contain the distance and one action. And an action can be taking a turn, or it can be getting onto a highway, etc. So let's talk about the the extreme gradient boost algorithm. This is an implementation of gradient boosted trees. So gradient boosting essentially is taking the derivative of the loss function with respect to the weights and updating the weights with this derivative. The gradient descent concept is fundamental to the gradient tree boosting algorithm, in which an ensemble of weak learners are combined to form a strong learner. And each weak learner is a decision tree, and the decision tree is grown iteratively, which distinguishes the gradient tree boosting method from random forest, for example. Each new decision tree addresses the shortcomings of the other weak learners in the previous iteration. Backwards tree pruning is used for each weak learner. Essentially, we look for a tree that will minimize the loss at each iteration, and backwards tree pruning avoids overfitting. Cross-validation is used to tune the hyperparameters for XGB. The XGB framework also allows for parallelization of the tree generations, and it caches gradient vectors, which improves the computational efficiency of the training. So the first two methods here, tree pruning and cross-validation, improves the learning efficiency, and parallelization and caching the gradient vectors improves the computational efficiency. So our objective function using the XGB method is the sum of the root mean square error loss plus a regularization term. We optimize some hyperparameters. Four hyperparameters are optimized by random search. Lambda, which is the weight on the regularization factor, does not appear to have a significant impact on the results of our XG boosting. Subsample size does appear to have an impact. Subsample size is essentially the amount of data that is sampled for each tree. And we have found that, or rather an 80% subsampling is optimum. Min-child weight is the minimum amount of data points within a particular node split in the decision tree before the decision tree terminates its splitting process. The eta is the learning rate for the algorithm. We see that a lower eta is more effective for the learning process. However, keep in mind that a lower eta means that the algorithm is learning slower, and therefore it takes more time to train. The final results of the XGB are as such. The training root mean square error is about 0.14. The validation using k-folds error is 0.37, as well as the Kaggle final test error is 0.37. This puts us at about the top 6 or 7% of the Kaggle leaderboard, which is a fairly good result. Next, I will give the presentation over to my co-host Abhinandan to talk about the neural network methods and the conclusions for the project.
Hi, I'm Abhinandan, and I will be continuing the machine learning presentation, starting off with neural networks. So, neural networks are a subset of machine learning, and they form the basis of deep learning algorithms. And for our project, a feed-forward network architecture was created, for which we used TensorFlow or Keras. And it is important to note that since the processed features did not have any geometric relationships or any time dependencies, we did not have to use convolutional or recurrent neural networks. And so all of the hidden layers in the network are dense or fully connected. Batch normalization layers were also used in order to improve the training stability and to allow for quicker convergence. And essentially, with batch normalization, the training data was batched, split in batches, and for each batch, the inputs were normalized with respect to their batch size and input size dimensions. So now I'll talk about the hyperparameters. There were 5 hyperparameters that we tuned. The number of dense or fully connected layers, which is the network depth, which is between 4 and 64 layers. Then we had the number of neurons per layer, which is the breadth, which is between 16 and 512 neurons. The optimizers, for which we used stochastic gradient descent or SGD, momentum, RMS prop, and ADAM, or where ADAM is also known as ADAM stands for the adaptive moment estimation. We also tuned the learning rate or alpha, where we tested values between 10 to the power minus 2 and 10 to the power minus 4. And we tried regularization. So first no regularization, then L2 and dropout or dropout regularization. As for the experiments, essentially random search was used for hyperparameter tuning, and we did not use an exhaustive grid search due to time and computational constraints. And we noted that the model was overfitting quickly, so the training was usually stopped at around 100 epochs. We initially experimented with different batch sizes of 16, 32, 64, and so on, but in the end, we chose a batch size of 128. This is because of the trade off between the number of gradient descent updates per epoch as well as the training time per epoch. And moreover, the dataset was quite large, more than 1.4 million examples, so this batch size is appropriate. And lastly, we used a train validation split of 80:20. And as for the results, this table summarizes our main results, and the best model is highlighted in green. So as we can see, from top to bottom, the performance or the loss improves. The loss is decreasing from top to bottom, and this is because firstly we switched from SGD to ADAM, and we also tried the other optimizers, but ADAM was clearly the best. Then we also noted that the error was decreasing with increasing network depth and breadth. So we went from 16 to 40 layers, and in this process, at each step, the loss was decreasing, the validation loss. Also, we adjusted the learning rate according to the optimizers we used. So for Adam, it was the alpha it was 1e minus 3, and lastly, L2 regularization helped improve the ability of the neural network to generalize to new data. So we noticed that the validation loss was improving. So with the final model that we highlighted previously, our private score on the leaderboard for the Kaggle competition was 0.39758, and the public score was 0.39963, so roughly 0.39. So clearly, the XGBoost performed better than neural networks for predicting the NYC trip duration. But why is that? The possible reasons are XGBoost has the big advantage of ensemble learning, while neural networks do not. So essentially, ensemble learners they use the power of individual learners, and for XGBoost, if the individual learners are very strong, then the XGBoost itself is very strong. And clearly, for this data set, actually ensemblers are very popular, and that demonstrates that XGBoost is a very good model for this data set. Furthermore, hyperparameter tuning could have improved neural network performance, but it was difficult to do so, as I mentioned, because of the computational and time constraints. And another thing to note is, while XGBoost does allow us to reach a top 6% Kaggle leaderboard rank, but higher performance might have been possible with some external data such as weather data in addition to OSRM. And lastly, a small reason for slightly less performance than we expected was that some taxis or drivers may be faster or more aggressive than the others. In that case, that would complicate the trip duration even further. So now I'd like to conclude this presentation. So to summarize, we have explored various techniques for exploratory data analysis to better understand the trends and patterns in the New York City data. We applied outlier detection using the interquartile range and z-score approach. We also performed feature engineering and selection on a data set, which is quite extensive. And for prediction, we experimented with two different types of models, XGBoost and neural networks. Our experiments and analysis showed that XGBoost outperformed the neural network models, and so we came to conclude that XGBoost is a great solution to the New York City taxi trip duration prediction problem. As for some challenges faced, briefly, the data was noisy and contained both outright errors and non-standard behavior. Then the trip duration was actually affected by various factors, such as time of day, speed, and trip distance. The data had relatively few features originally, per training example, and so the external data was required. Training of the machine learning and deep learning models was computationally expensive and time consuming, and the division of work was difficult due to dependencies between different aspects of our project. So how did we solve these challenges? We discovered ways to filter bad data to improve the prediction accuracy. We explored factors and created new features to account for these factors. We used the NYC OSRM dataset from Kaggle, though processing and merging with the original data was somewhat challenging. We also had to use cloud services for computation, such as Google Collaboratory and Kaggle GPUs. And lastly, we attempted to collaborate on the code by sharing code on a group GitHub repository and by using Google Collaboratory. And lastly, some possible future improvements for this project of ours. First, we could have tried different methods. We can try different methods in the future for outlier removal and data cleaning. This is because there are probably still more anomalous data, and so if we had removed this data, it would have generalized better. And we could have also engineered more and hopefully better features, and in the end, selected features more carefully in order to better train our data, train our models. And lastly, we can also experiment with some other complex models to see if the performance is better. So some models such as cat boost or light gradient boosting, so light GBM, and so on. And that concludes our presentation. Thanks for watching.